Welcome, everyone, to another deep dive. Today, we're digging into a chapter all about special products and expansions in algebra.
That's right.
Our mission really is to sort of extract the core ideas, the shortcuts, the patterns that this text highlights.
Exactly. Things that let you handle certain multiplications and problems, much more quickly than the standard way. Think of it like finding the express lane in algebra.
Okay, express lane, I like that. So the text kicks off with the basics, right? Like multiplying two binomials, something like x plus a times x plus b.
Yeah, it sets the foundation there. The key takeaway is the structure of the result. You always get x squared.
Right, the first term squared.
Then you get a middle term, which is x multiplied by the sum of a and b.
Ah, so the constants added together times x.
Precisely. And the last term is just the product of a and b. So like the example x plus 5, x plus 3, it's x squared plus, well, 5 plus 3 is 8, so 8x.
Plus 5 times 3, which is 15. So x squared plus 8x plus 15.
Exactly. And that middle term, the 8x, it comes from adding the outer product x times 3 and the inner product 5 times x. It's systematic.
Okay, seeing that structure helps. And that leads directly into some really useful shortcuts the chapter emphasizes. What's the first big one?
Probably the most elegant one, I'd say. The product of the sum and difference of two terms. The classic a plus b, ab.
Yes. And the result is just, it's incredibly clean. A squared minus b squared.
That's it.
Why does it simplify down so much? It seems almost too easy.
Well, that's the beauty of it. If you actually multiply it out using FYL first, outer, inner, last, you get a times a, which is a squared.
Okay.
Then the outer is a times minus b, so minus ab.
Uh-huh.
The inner is b times a, so plus ab.
Right, plus ab.
And the last is b times minus b, so minus b squared. You have a squared minus ab minus b squared.
Ah, and the minus ab and the plus ab, they just cancel out.
Exactly. They vanish.
Both.
Leaving you with just the first term squared minus the second term squared.
That's fantastic. So if you see something like the example 5x plus 4y times 5 by 4y.
You instantly recognize the pattern.
Yeah.
A is 5x, b is 4y.
So it's just 5x squared minus 4y squared.
Which is 25x squared minus 16 squared. Done. No intermediate steps needed if you spot it.
That saves a lot of time. And, the text shows this isn't just for variables. It works brilliantly with numbers, too. Like 107 times 93.
Right. Instead of grinding out the multiplication.
You see it as, wait, that's 100 plus 7 times
4.
1.
Yeah, perfect fit. A100, B7. So the answer is just 100 squared minus 7 squared.
Which is 10,000 minus 49. Easy calculation. 9,511.
Yep. Almost mental math.
Yeah.
Compared to the alternative. It really shows the power of pattern recognition.
Okay, super useful. Then the chapter moves on to squaring binomials, things like a plus b squared and ab squared.
More patterns, more shortcuts. For a plus b squared, the expansion is a squared plus 2ab plus b squared.
And for ab squared.
Very similar. A squared minus 2ab plus b squared, the key difference is that middle term sign.
That middle term, the 2l, it's twice the product of the two terms inside the bracket. That seems to be the crucial part people might forget.
It is. It's not just squaring each term. You always have that middle piece. So for, say, 3x plus 4y squared.
Okay, so following the a plus b squared pattern, a is 3x, b is 4y, so we get 3x squared.
Plus 2 times 3x times 4 plus 4y squared.
Which works out to 9x squared plus, let's see, 2 times 3 times 4 is 24. So 24y plus 16y squared.
Exactly. 9x squared plus 24y psi plus 16y squared. Again, a direct formula application.
And like before, this has numerical tricks too. The example is squaring 208.
Yeah, instead of 208 times 208, you think of it as 200 plus 8 squared.
Applying the a plus b squared formula again.
Right, so 200 squared plus 2 times 8 plus 8 squared.
That's 40,000 plus 2 times 200 is 400 times 8 is 3,200 plus 64.
Add them up. 40,000 plus 3,200 plus 64 gives you 43,264. Way easier than long multiplication.
It really is. The chapter also briefly mentions cubes, right? Like a plus b cubed.
It does, yeah. Just notes that there are similar defined formulas for a plus b cubed and ab cubed, following the same idea of predictable expansions. We won't dive deep there, but the principle holds.
Okay, but then there's this interesting section, application of formulae. It suggests these aren't just for expanding.
Exactly. This is about using the formulas almost in reverse, or, well, as a bridge. If you know some values, you can use the formula structure to find others.
Like the example they give. If you know what a plus b equals and what ab equals, you can find a squared plus b squared.
Precisely. Let's use their numbers. Say a plus b equals 8 and ab equals 15. How do you get a plus b?
Okay. Well, we know a formula that connects these. A plus B.
Right, A plus B equals A plus 2A plus B. Or you can write it as A plus BL plus, and AB is 15, so we can substitute those in.
Yep, so 8 on the left side equals the A plus B we're looking for, plus 2 times 15 on the right.
Okay, so 64 equals A plus B plus 30.
Now it's simple. Subtract 30 from both sides. And you get 8A plus B equals 34. Wow! So the formula lets you find a value indirectly.
That's the core application idea, using the known structure to find unknown pieces.
So if we boil down this whole dive into the chapter, what's the absolute main takeaway?
I think it's really the sheer utility of pattern recognition in algebra. Seeing these special products or expansions isn't just about memorizing formulas.
It's about seeing the underlying structure.
Exactly, and realizing that structure gives you a shortcut. It bypasses tedious work, simplifies number crunching, and, as we just saw, even helps you find related values indirectly.
It transforms potential slogs into quick steps just by recognizing, oh, this fits the pattern.
It makes algebra feel less like a series of disconnected problems and more like a system with recurring exploitable patterns.
Which really gets you thinking outside of algebra, maybe even in, everyday life or other fields.
Yeah.
Where else might spotting one of these underlying patterns suddenly unlock a massive shortcut or give you a much deeper insight into what's actually going on?
That's a great question to ponder. That principle definitely applies broadly.
Something for all of us to keep an eye out for.